Asteroids, moons, and planets hold vast reserves of precious metals and valuable resources waiting to be discovered and utilized. We often hear about the potential riches locked away in these celestial bodies, tantalizing us with the promise of untold wealth. Why then haven't we started tapping into this cosmic treasure trove? What holds us back from reaching out and claiming these resources? The answer is a complex mix of technological, economic, legal, and environmental challenges. Each of these factors presents significant hurdles that must be overcome. Bringing resources back from space is currently a bridge too far, a monumental task that we are not yet equipped to handle. Space is a hostile and unforgiving environment with extreme temperatures, radiation, and microgravity posing constant threats. The distances are immense and the costs are astronomical. The financial investment required is beyond the reach of most current budgets. Simply reaching these resource-rich locations requires advanced technology and massive amounts of energy, pushing the limits of our current capabilities. Extracting and processing the materials in the vacuum of space presents further complications, as traditional mining techniques are not viable in such conditions. Returning these resources to Earth adds another layer of complexity and expense, involving intricate logistics and safety measures. While the idea of space mining captures the imagination, the reality is far more challenging than it seems, requiring breakthroughs in multiple fields. The dream of bringing space resources back to Earth remains elusive for the foreseeable future, a goal that continues to inspire and drive innovation. However, the pursuit of this goal has spurred innovation and advanced our understanding of space, leading to new technologies and methodologies. The knowledge gained from these endeavors will undoubtedly benefit future space exploration, paving the way for the next generation of explorers and scientists. The allure of space mining lies in the sheer abundance of resources scattered throughout our solar system. Asteroids, for instance, contain vast quantities of platinum group metals, water ice, and other valuable materials that are rare on Earth. These resources could potentially fuel future space missions, provide essential materials for building space habitats, and even address resource scarcity on Earth by supplying rare metals. However, the challenges are equally immense and multifaceted. Extracting resources from asteroids requires specialized robotic spacecraft and mining equipment, which must be incredibly durable and reliable. These machines must be designed to operate autonomously or with minimal human intervention in the harsh environment of space, where maintenance and repairs are extremely difficult. Transporting these massive pieces of equipment to distant asteroids is a logistical nightmare, involving complex calculations and precise timing. Once extracted, the raw materials must be processed and refined, which is no small feat. This process requires energy, which is a precious commodity in space, often harvested from solar panels or nuclear reactors. Furthermore, refining in the vacuum of space poses unique technical challenges, such as dealing with extreme temperatures and the absence of gravity. These difficulties contribute significantly to the overall cost and complexity of space mining, making it a high-risk, high-reward venture. Furthermore, the ethical and legal implications of space mining remain largely undefined, raising questions about ownership and environmental impact. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but the specifics regarding resource extraction are still debated among experts. The lack of a clear legal framework adds another layer of complexity to the already challenging field of space mining, necessitating international cooperation and new regulations. Operating in the vacuum of space presents numerous technological obstacles that are unlike any challenges faced on Earth. The extreme temperature fluctuations, radiation exposure, and lack of atmosphere create a hostile environment for both humans and machines. These conditions can cause equipment to malfunction or degrade rapidly. Developing equipment that can withstand these conditions is a significant challenge. Engineers must rigorously test materials and designs to ensure they can endure the harsh space environment. Microgravity also poses a major problem for mining operations. Without gravity, traditional methods of separating and moving materials become ineffective. Traditional mining techniques rely on gravity to separate materials and facilitate movement. In space, innovative solutions must be developed to replicate these processes in a weightless environment. In the weightless environment of space, new methods must be devised to handle and process extracted resources. This includes the use of robotic arms and other automated systems. Another hurdle is the sheer distance between Earth and potential mining sites. These sites are often located on asteroids or other celestial bodies far from our planet. Transporting equipment and personnel to these locations takes significant time and resources. The logistics of such missions are complex and require careful planning. Communication delays also complicate remote operations and require a high degree of autonomy for robotic systems. These delays can make real-time control difficult, necessitating advanced AI and autonomous technologies. The development of advanced robotics, autonomous navigation, and resource processing technologies are crucial for overcoming these technological hurdles. These innovations will enable more efficient and effective space operations. Significant advancements are needed before space mining can become a practical reality. Scientists and engineers are continuously working on new technologies to make this vision possible. The economic feasibility of space mining is a major concern. The initial investment required for developing and launching mining equipment is enormous. The cost of transporting resources back to Earth adds further to the expense. The current cost of launching payloads into space is prohibitive for large-scale mining operations. Reusable launch vehicles and other cost-reducing technologies are essential for making space mining economically viable. The market value of space-mined resources is also uncertain. While some asteroids contain valuable materials like platinum, a sudden influx of these resources could depress market prices and render the entire venture unprofitable. The economic risks associated with space mining are substantial. Investors are hesitant to commit large sums of money to a venture with such high upfront costs and uncertain returns. Until the economic landscape becomes more favorable, space mining will likely remain a distant prospect. Section 5. Market mayhem, potential impacts on Earth's economy. The introduction of space-mined resources could have a disruptive impact on Earth's economy. A sudden influx of rare metals, for example, could drastically lower prices and affect the profitability of existing mining operations. Certain industries that rely on these resources could benefit from lower prices. However, the overall economic impact is difficult to predict and could lead to significant market instability. Governments and international organizations need to carefully consider the potential economic consequences of space mining. Regulations and policies may be necessary to mitigate the risks and ensure a smooth transition. The potential for market disruption is a significant factor in the current hesitation towards space mining. Careful planning and international cooperation are essential to navigate the economic complexities of introducing space-mined resources into the global market. Section 6. Who owns the cosmos? Legal quandaries of space resources. The legal framework surrounding space resource ownership is complex and evolving. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but the interpretation of this treaty with regard to resource extraction remains ambiguous. Several nations and private companies have expressed interest in claiming ownership of space resources. The lack of a clear legal framework creates uncertainty and could lead to international disputes. The development of a comprehensive international legal framework is crucial for the sustainable and peaceful development of space resources. This framework should address issues such as ownership rights, environmental protection, and profit sharing. The legal complexities surrounding space mining are a major obstacle to its progress. Establishing clear legal guidelines is essential for encouraging investment and ensuring the responsible use of space resources. Section 7. Living off the land In-Situ Resource Utilization, or ISRU. In-Situ Resource Utilization offers a more practical alternative to bringing resources back to Earth. ISRU involves using resources found in space to support space missions, such as generating fuel, building habitats, and providing life support. ISRU could significantly reduce the cost and complexity of space exploration. By utilizing local resources, missions can become less reliant on Earth-based supplies and extend their range. Water ice found on the Moon and asteroids can be used to produce rocket propellant and drinking water. Regolith, the loose surface material on the Moon, can be used as construction material for habitats and landing pads. ISRU is a key enabling technology for future space exploration. By reducing our reliance on Earth-based resources, ISRU can pave the way for sustainable and long-duration space missions. Section 8. Space mining's future, a long but promising journey. While the challenges are significant, the potential benefits of space mining are too great to ignore. As technology advances and the cost of space access decreases, space mining could become a reality in the future. The development of advanced robotics, reusable launch vehicles, and in-situ resource utilization technologies are crucial for the future of space mining. International cooperation and a clear legal framework are also essential for the responsible and sustainable development of space resources. Space mining holds the promise of unlocking vast resources and enabling humanity to expand its presence in the solar system. While the journey is long and challenging, the potential rewards are immense. Section 9, Conclusion. A bridge too far, for now. Bringing resources back from space presents a formidable challenge. The technological, economic, and legal hurdles are substantial, and require significant advancements before becoming feasible. In-Situ Resource Utilization offers a more practical approach for the near future, enabling sustainable space exploration and reducing reliance on Earth-based resources. While the dream of mining asteroids and bringing treasures back to Earth remains alluring, it is a bridge too far for now. However, the pursuit of this dream continues to drive innovation and expand our understanding of the cosmos.